Cabin the X. Welcome back to another COMSOL Multiphysics tutorial with Cabin the X. Today's tutorial is about water hammer. So let's imagine that we have a pipe filled with water. When a valve is suddenly closed, this creates a pressure wave or a hydraulic transient that travels through the pipe. This pressure surge, often referred to what we call water hammer, can generate extreme pressure spikes, and this can cause severe pipe failures. In this figure, this represents a typical pressure wave caused by a closing valve in a pipeline. In regards to our model definition, we have a reservoir represented by P0, and that's 1 atmosphere. We also have a length of pipe 20 meters, and the radius of that pipe is 398.5 millimeters. We have a valve at the far end of our pipe where we have Z0 here that represents the location of the pressure sensor measurement point, and that's 11.15 meters. The wall thickness of our pipe is 8 millimeters, and we must also consider the material, which is steel, and the Young modulus, which is 210 gigapascals. The speed of the pressure wave is determined by the compressibility of the water and the elasticity of the pipe. It's calculated using this formula. Also, we need to consider the Tchaikovsky's equation. This calculates the amplitude of the pressure surge based on the water density, the wave speed, and the average fluid velocity before the closure of the pipe. The Courant-Friedrichs-Lewy condition, CFL, and the potential for Gibbs oscillations are important considerations when numerically simulating water hammer events. By carefully selecting the mesh size and time step and using the appropriate numerical techniques makes it possible to obtain accurate and stable conditions. And for our global definitions parameters, here they are. I'll provide this via a text file, and I'll put the link in the video's description so you can have access to it. Now that we have COMSOL Multiphysics up and running, let's navigate to the model wizard. For space dimension, let's use a 3D space. Let's navigate down to fluid flow. And let's expand single phase flow. And let's select water hammer. Let's add that. So that's our physics. And let's add our study under general studies, time dependent. Done. Let's add our global definitions parameters. These parameters are what we're going to use throughout our study. So model builder, global definitions, parameters. Let's load that. Let's come here, click on that, navigate to wherever you have this text file stored. Open. And let's now navigate to our toolbar. Let's click on geometry. Let's expand more primitives. and let's click on polygon. Now let's create our geometry by entering the necessary coordinates. Everything we're going to create is going to be on the x axis, so we're going to start at 0, of course, and here we're going to enter our first parameter, so our measurement point. You can come here and you can copy it if you don't remember it, but it's C0, and navigate back to the geometry. You can enter that here, and the y and the z will be 0 as well, and the L. So you can navigate back to your parameters, and we know the L is our pipe length. To polygon, the y is 0, z 0, and once you enter those, let's build all objects. Now let's add our material. So from the home toolbar, navigate to add material. Let's expand built in, and at the bottom of built in you should have water liquid. Let's add that to component. Let's close this. So with that added, all the fluid properties would be selected automatically, and the material parameters are retrieved from the water material. Okay, so everything here is added automatically. Now let's go over to our pipe properties, and on the pipe shape right here, let's choose circular, and for the inner diameter, that would be 2 times the radius, and for our pipe model, where we have Young modulus here, let's change that to user defined. Let's enter caplocks E right here, and for the wall thickness, let's enter lowercase w. Okay, now we get back to our parameters. So here we have E, which is our pipe's Young modulus. We have W, that's our pipe wall thickness. And prior to that, we entered our C0, that was our measurement point. So let's now get back to pipe properties and double check everything here. That looks okay, except for our flow resistance. So we need to change that, the friction model and the flow resistance. Let's change that to user defined and leave it as is. Let's now navigate to our initial values, and for our initial values for the pressure, let's enter P0 and U0. Okay, so if we navigate back to our parameters, so here we have P0, that's our initial pressure, and U0, that's our initial velocity. Okay, let's go back to initial values. Now we need to add our pressure, so let's navigate to the physics toolbar, and where we have points, let's expand that and let's add pressure. So for our pressures, let's select point 1, and for the pressure value where we have P in right here, let's enter P0, and we need to build our mesh now. So let's navigate to our mesh toolbar, and where we have more generators, let's expand that, and let's select edge, and let's click inside here. Let's key in Ctrl A on the keyboard, so let's select both edges, and let's navigate to our model builder. Let's click on size, and where we have our general physics, under that we have predefined normal, let's change this to custom, and the maximum element size, let's put that uppercase, let's put uppercase L over uppercase N. So if we go back to our parameters, L is our pipe length and N is the number of mesh points. Okay, so let's go back to size. So the maximum element size, L divided by N. The minimum element size, let's just put that as 1. And let's put our expression, or unit, sorry. So that would be millimeters. Okay, and let's now click on build all. Now let's create our study. Now let's navigate down to our study. Let's minimize component 1 and focus on our study. On the study, let's click time dependent, and for our range, let's change those values. So we'll use these values, and let's navigate to our study toolbar, and we need to add show default solver. Let's expand that. Let's click on time dependent solver 1, and let's expand time stepping, and for steps taken by solver, let's change that to manual, and for the amplification for high frequency, let's enter 0.2, and we need to make another change, and let's change the time step to dt. So if we go back to our parameters, dt is our time step according to CFL. Let's go back to our time dependent solver, and for our next step, let's just compute. So if we compute here, that might take a minute or two. Now that our computation is completed, let's go to zoom extents. Now this shows us the pressure along the pipe at T equals 0.24 seconds. Now let's create a few plot groups. So let's go to our results toolbar, and let's select 1D plot group, and let's call this plot group measurement point, and let's right click on that, and let's select point graph. So here for selection, if yours is off, you might get this little warning here. You can simply turn it on, and you need to select point 2. Point 2 would be the middle point right here. Okay, and for the y-axis data, let's just add minus P0, and all you have to do now is just click on plot. So this point graph shows us the excess pressure history measured at the pressure sensor. Let's create another plot group. So you can do that from the results toolbar right here. 1D plot group, and let's call that one valve. Let's right click on valve. Let's create another point graph, and for our point, that would be point 3 right here. Our expression would be the same, minus P0. Okay, now let's right click on point 1 graph. Let's duplicate that, and for point graph 2, we need to change the expression for the y-axis data right here, so that would be a different expression. So it would be this. Now let's hit plot. Let me plot right here. So the instantaneous closure of the valve results in a water hammer pulse of amplitude given by Joukowski's fundamental equations. Let's now create another plot group. So let's go back to results, 1D plot group, and let's call that one pressure profile. So inside of our label, let's call it pressure profile, and let's create a line graph. So let's right click on pressure profile, let's select line graph, and let's click inside here, Control A, so that will select both of our edges. And for the y data expression, let's put minus P0, sorry. And for the time, we need to go back to pressure profile, and where we have data time selection, we need to select the last time selection, because all of this will be difficult to comprehend. So we'll just focus on the last one, and let's hit plot. Here we can see the excess pressure along the pipe at T equal 0.24 seconds. This concludes this particular tutorial. Thank you for your time. Bye for now.